The classical versus quantum traps module allows us to compare a classical system with a quantum system. The classical system consists of a ball that rolls without slipping on a given ground. The ground is composed by a harmonic wall and a Gaussian barrier, and it can be shaped by moving the slides on the right. We can choose the initial conditions by changing its position and velocity, and we are also allowed to change the ball's radius. Additionally, we can choose between two numerical methods to solve the Lagrange's equation. After hitting the compute button, we can run the video with the play, pause, stop and video velocity buttons. Then we can check the total energy conservation, which is the sum of all the different energies. The quantum system consists of a Gaussian wave function in a given potential. The plot shows the probability density of the particle's position in red. The potential is plotted in dark green, and in light green we can see the average energy. Similarly, we can shape the potential with the slides on the right. As in the classical system, we can choose the initial position and the momentum. Here, we can choose the Gaussian's thickness and choose between two usual particles of different scales. We must again hit the compute button before watching the video. What we can do here is to check the norm conservation, which should always be 1, except for computing noise. Some demos have already been prepared to show interesting situations. First, we can place the ball on the left side of the wall with not enough energy to overcome it. The red line shows its energy, that is, the maximum height it can achieve, and if it is beneath the maximum, our classical particle will never be able to reach the other side. However, in the quantum case, things get quite different. Let us place our Gaussian completely on the left side of the wall and with an average energy lower than the peak. After a while, the Gaussian completely gets to the right side, and since the probability of finding the particle on the right is 100%, we can state that it has crossed the wall by the quantum tunnel effect. The double well demo splits the Gaussian in two smaller portions, as if it splitted the particle in two. Nevertheless, remember that we are dealing with probabilities, thus we have a 50% of finding it on each side. Whereas in the classical case, the ball eventually falls to just one side of the wall. The equilibrium demo sets the ball in a minimum energy state, leaving the classical particle motionless. If we displace it, we get the usual movement of the harmonic oscillator. This is similar to the evolution of an eigenstate, a particular wave function that, for a specific potential, doesn't evolve with time. If we displace it, it doesn't change its shape, but moves as the classical particle does. Finally, another interesting case is the dispersion of the wave function when no potential is applied to it. We can see how the free particle expands and uniformly distributes its probability, something unbelievable for a classical particle. The classical system allows one more interesting topic, which is the comparison between two numerical methods for solving differential equations. Using the simple Runge-Kutta 4 method, we are not able to compute the movement since the ball loses energy. However, we are indeed able to do so using a finer method, the Runge-Kutta Feldberg method. This takes longer to compute, but the result is satisfactory in that the ball keeps its total energy constant. We have quickly covered the main features of this module, but many other possibilities are waiting for you to explore them.